So that was the insertion and deletion operation of the binary heap. And the insertion and deletion operations are everywhere in every data structure. And that was basic. Here, in this slide set, we are going to one more special operation of the binary heap. It's being called a build operation. And this build operation is turning an unsorted, unstructured array into the binary heap. So, for example, let's consider these three structures. But let's imagine that this is stored in terms with utilizing the array. So basically, in the index of 1, 2, 3, 4, 5, and it stores 2, 3, 4, 5, 6, etc. And what you want to do is turning this unsorted binary heap as an array, into a binary heap, binary maxi heap. And one way is that we just insert these n values one at a time, right? And the insertion complexity actually itself is it takes the percolate up, right? Percolate up. So is the insertion complexity is order of log n, because that it might reach to the root in the process of the percolation. So it will take order of log n operations. And we are inserting these values for n times. So to build a binary heap, it will take order of n log n. This is called naive build. It's just a simple utilizing the insertion operations that we did just like in the other data structures. But if we have an array of data which is not sorted in as a binary heap, what we can do is that we can choose to use the alternative build approach. So alternative build approach works like this. So this is a simple process of the alternative build. Okay, let's just erase this. And we start from the 16, from the last element. And what we are going to do is the percolate up. But just one time percolate up. So to percolate up of this 16, it has to compare it to the 8. And actually, heap property is broken. So what we are going to do is exchanging 16 with 8. 16 with 8. Right? And then this is done. This is done. Right? And then we move to the next element here, 15. And 15 compare that to the 16. It's just one time percolation up. And yeah, we don't have to percolate up because heap property is kept, at least in terms of this small tree. So 15 is done. So we move to this 14, right? So it means that we are going backward in terms of the array index. We start from the maximum array index to this to the index of 1. That's what we are going to follow. So move to the 14, and if we watch this 14 and if we do the one time percolate up, we have to exchange the 14 with 7. So 14 with 7. So that's what happened. And we move to this 13, and 13 is already 14 is up, so 13 don't have to percolate up. So this tree structure is kept as the keeping the heap property, and this tree structure is keeping the heap property. And if we move to the next, we do the same, and heap property is kept. And if we move to this next thing, then this heap property is all kept, at least at this level, right? And I will erase for a second. And then what you want to do is then going to 9 to the, if we're going to the backward of the index, then the next element is going to be this 8, right? But 8 is not 8, it's actually 16 because that is already percolate up, it has happened. So if we do the one-time percolate up, 16 is compared to the 4, and 16 should be go up, right? 16 should go up. And then after doing that, 16 is here, 4 is here. But the percolate, this violates this tree's heap property, right? So this 4 is going to be exchanged to the maximum child, the bigger child of 15. So 4 is going to be here and 15 is going to be here, right? So that's the percolate up, one-time percolate up of this 16 happened, right? And the same thing happens here. So if, and then after that, 14 doesn't have to percolate up, so it stops there. And then moving to the 12 and 3, 12, right? So 12 needs to go up. So 12 needs to go up and 3 goes down. But also that breaks the heap property of this triangle. So it takes a bigger child to percolate down furthermore. So 3 is going to be here and 11 is going to be upward. So 12, 11, 3 is now here. And 10 doesn't need to go upward, right? Because 12 is already here. So this tree's heap property is kept, and this tree's heap property is kept, right? And after that, let's erase it for a second. After doing this tree-wise operations, right? And then what we want to do is those percolate up. So 16 needs to percolate up, and then it compared to the percolate 2 with 16, and it needs to percolate up. Then what happens is that 16 is exchanged with 2. And now 2 is here, but the heap property is broken, and then it takes the bigger child. So 15 goes up, and 2 goes down here, and 4 goes up, 2 goes down here. So what happens is that 8 goes up, so 8 is bigger, 8 is bigger child, so 8 goes up, and 2 is going down here. So what actually happens is that 16 is now here, and 15, 8, and 2 is now here, right? And then now we go to here, and 12 doesn't need to go upward because 16 is already there, so heap property is kept. So here, this binary heap is constructed. Now it keeps the shape property as well as the heap property, right? So we did hold this one-time percolate up process a while, right? And that was really different from the insertion operation utilizing the naive build operations. So naive build basically just to utilize the insertion operations and insert for n times. So it took order of n log n times. So an alternative build used a little different approach, doing one-time percolate up process and making the heap, growing the heap property bigger and bigger, and cover the whole tree with the heap property at the end of the day. And if we take this alternative build approach, there should be some kind of benefit for it, right? So then what's the benefit? Actually, there is one astonishing fact here. That kind of surprising fact here is that it's complexity of this alternative build method. So if we have a full tree, size of n and height of h. So h is log n. Let's imagine. We assume that each node in the tree alright is positioned through the percolation down of a worst case, right? So one-time percolate up was constant, but there was consequent percolation down happened sometimes, right? And if that percolation down happens, the maximum percolation down operation is going to be h. So so from the root node, h percolation happens. And the node at I, height I, takes h minus I percolation down happening, right? Node at height I takes maximum h minus I percolation down. And let's count how many percolation down occurs. Because the percolation up is always constant one-time operation. One-time operation means that it will take n operation anyway. There is n number of percolation up. But we don't know how many percolation down will happen. So we need to count the percolation down numbers. And we know that node at height I takes h minus I percolation down. So for example, level 0, which is the root case, it takes maximum, in the worst case, it takes h percolation down. And there is only one node here, root node. So h multiplied by one time. And level 1, we have two nodes which takes h minus 1 percolate down. And level h minus 1, it will take, 2h minus 1 child, but it will take just one time percolate down, right? So, means that we have, if we are going to sum these things, what happens is that h multiply 1 plus, right, h minus 1 multiply 2 plus h minus 2 multiplied 2 plus plus h minus, right, h minus 1. That's going to be plus. And 2 h what? Minus 1, right? And if you are going to add up all these things, then it will look like this. And this is, you can understand with this summation, we know that this is right. But the things that you may not comprehend at the moment is that why it takes O of n. Actually, it takes O of n. And there is proof for that. And what we are going to do in the offline classroom is that we are going to prove this of this alternative build. Alright? So, why we are taking this alternative build approach, one-time percolate up and percolation down, consequence is that it actually can reduce O of n log n time of build to the O of n. Right?